In today's lecture, we will discuss the calculation of net iron length and MMF required for teeth. First of all, we'll discuss net iron length. The magnetic cores of electrical machines are often built with laminated steel plates, as shown in figure. These laminations or stampings are insulated from each other. Moreover, the length of the core is divided into packets as shown in figure. This is one packet, this is second packet, and this is the third packet. So in between there will be radial ventilating ducts for better cooling. So thus irregularities are created in thickness of laminations. So it is very important to calculate the net iron length. Here the capital L is the actual length of core, but this is not the net iron length because iron part is only the laminations. Let's define a term which is related to the net iron length, that is stacking factor. It is the ratio of actual length of iron in a stack of assembled core plates to the total axial length of stack. So let's define the terms. Gross core length, B capital L. Gross core length is the length of core measured along the axial length of core. Then gross iron length. Gross iron length LS is equal to core length, that is capital L, minus, this is the core length, minus the length of ventilating ducts. So that is equal to L minus NdWd, where Nd is the number of ventilating ducts. In this case it is 2. And Wd is the width of each ventilating duct. This is the value of Wd. So this will give the total length of ventilating ducts. Then the net iron length Li is equal to Ki into L minus NdWd, where Ki is the stacking factor for iron, which is normally taken as 0.9. So by definition, Ki is equal to Li divided by L minus NdWd. Now we will discuss the calculation of MMF required for teeth. In the previous lecture, we had discussed the calculation of the MMF required for air gap. Similarly, it is very important to calculate the MMF required for teeth portion also. But the problem is the teeth is not having a uniform shape from top to bottom. That makes it difficult to calculate the MMF required for teeth. The calculation of MMF necessary to maintain the flux in teeth is difficult due to the following complex problems. First is the teeth are wedge shaped or tapered when parallel sided slots are used. Thus, flux density is not constant over the length of teeth. Second case, the slot provides another parallel path for flux. So, it shunts the path through tooth. That means the flux passes through tooth as well as slots. As a result, an appreciable portion of the flux goes down the depth of the slots. These two are the major issues that makes it difficult to calculate the MMF required for teeth. So we have different methods to calculate the MMF. Next we will discuss the different methods. So the following are the methods usually employed for the calculation of MMF required for tapered tooth. First one is graphical method, then 3 ordinate method or Simpson's rule, then BT 1/3 method. The first method is graphical method. As we know, the MMF is given by H into L, where H is the magnetizing force and L is the length of magnetic path. So first of all we have to find H. The mm per meter, that is h, or otherwise denoted by small letter at, for the whole length of the tooth is not uniform, as the flux density is not the same everywhere. This is because the flux density is equal to flux by area, and the area cross section of tooth will be more at the bottom and less at the top. So, due to the irregularity of the shape of the tooth, the flux density is also not uniform. So, due to this fact, we have to get a mean value of h or mean value of at in order to find the MMF. So, to obtain the accurate value of the total MMF, a graph is constructed showing the variation of AT or variation of H over the length of tooth. The mean ordinate of this graph gives the equivalent AT for the whole of the tooth. Then, the total MMF required for tooth AT is equal to mean ordinate into height of tooth. That is AT mean into LT. That is MMF is equal to H into L. That is the equation. Or AT mean into DS. Here LT is the length of tooth and DS is the depth of slot. Both are equal. Then next let's see how the value of AT mean is calculated. That is how H is calculated. The mean value of H. For that purpose, we have to plot a graph which shows the variation of flux density. So let's consider this teeth. Here the teeth is having more thickness at the bottom and it becomes tapered at the top. So here the area of cross section is less, here the area of cross section is more. That means the flux density will be less at the bottom and flux density will be high at the top. So the variation of flux density is plotted as a graph. So here flux density is less and here the flux density increases as we go to the top of the teeth. So this is the graph to be plotted for flux density. Then the corresponding values of AT, that is H, corresponding values of AT is also plotted according to the material used for the teeth. The corresponding values of AT are found from the BAT curve, that is BH curve of the material and are plotted. So we will get a plot like this. Then the value of AT mean is obtained from the graph as shown. This is the mean value, that is the average value of this curve is calculated. The second method is three ordinate method or Simpson's rule. This method can be applied to teeth of very simple form and of a small taper. So this is a teeth with a small taper and it is a very simple form. It's having a very simple form. Here this is the length of teeth or depth of slot. Both are equal. So this method is based on the assumption that the curve relating AT with flux density, that is BH curve, is a parabola. The values of AT are obtained at three equidistant points, that is the values of AT at this point and this point, that is the ends of tooth and at its center. This is one end, this is the other end and this is the center. So the values of AT at these three equidistant points are noted, and then the mean value of AT is given by AT mean is equal to 81 plus 482 plus 83 whole divided by 6. This is the method to calculate AT mean in Simpson's rule. The third method is BT 1/3 method. This method is applied to teeth of small taper. This is a very simple method also, based upon the assumption that the value of 80 obtained for flux density at a section 1/3 of tooth height from the narrow end is equal to 80 mean. This is an assumption, but it's a very accurate method also. This method is very simple of all the methods, and results are sufficiently accurate if the teeth are worked at a low saturation. Next, let's see how the calculations are done. Let Bt 1/3 is equal to the flux density at 1/3 height from narrow end. Then 80 1/3, that is the magnetizing force at 1/3 height, is equal to the value of mmf per meter for Bt 1/3 as obtained from the BAT curve. BAT curve means BH curve of the material used for tooth. Therefore, the total mmf for tooth, that is 80 suffix T. 80 denotes mmf and T means tooth. So mmf for tooth is equal to 80 1/3 into LT is equal to 80 1/3 into ds, where LT is the length of tooth and ds is the depth of slot. Both are equal. Thank you.